In this video, we're going to talk about pointers. Pointers are usually a difficult topic for students. Actually, some students say this is the most difficult topic in the course. I'm going to try to make it as painless as possible. So first, we're going to talk a little bit about the memory model to give you the background behind pointers. And then we're going to go over some examples of basic usage of pointers. Okay, so imagine the memory of your computer as a really long tape composed of cells. Each cell can hold 1 byte or 8 bits of information. And each cell is labeled by an address, an integer address. So I've written the addresses here in the blue letters underneath the cells. So the address is just a way for us to refer to a place in memory. So we can say, go and get the information written in cell number 15, for example. So on a 64-bit processor, which probably most of us are using these days, a memory address is a 64-bit integer. So we have the potential to label up to 2 to the 64 mini memory cells. Okay, so we said that a char typically is 1 byte, is represented with 1 byte. So a char is just going to take up a single cell of our memory here. An int typically takes 4 bytes, so that's going to take up 4 cells of our memory. And a double is typically 8 bytes, so that's going to take up 8 cells of our memory. So in this example, let's say that we have a variable, an int variable named x, which is the number 184937267, and that's sitting in cells 11 through 14 of our memory. So at addresses 11 through 14. And in C++, we can actually see the address of a variable with the ampersand operator. So this is called the address operator. And what this is going to do is it's going to return the address of the first byte that the variable occupies. Okay, so in our example, x sits in memory cells 11 through 14. So the first cell it sits in is 11. So if we take the address of x, that's going to return 11. Okay, so that's our little toy pictorial example here. We can also see this in real code. So here's a code snippet where we define an integer variable x, and then we print out the address of x. Okay. So this is going to print out some number. Usually it's given in hexadecimal. So when I ran this on Godbolt, it printed out 0x7FFF blah blah blah. Okay, so the 0x just indicates that what follows is given in hexadecimal. And then if you count it, there's actually 12 hex digits that follow. Okay, so a hex digit can take on 16 possible values. Hexadecimal means 16, so it can take on 16 possible values. So that means that it holds 4 bits of information. Okay, and I said that there's 12 digits here. Following the 0x, there's 12 digits. So that's 48 bits of information. But we just said that an address should be 64 bits, right? So what's going on here? Well, current machines usually don't make use of 2 to the 64 cells of memory. So usually they just abbreviate addresses to 48 bits. Okay, so the high order 16 bits are just fixed. So they're just omitted. They're always the same. Okay, so that's why typically an address will be printed out. It'll just be 12 hex digits. Okay, and of course we have no control over where x is going to be stored in memory. So if you run this yourself, you're most likely going to see a different address here. Okay, so finally we come to the dreaded pointer. So when you're thinking about pointers and you're getting confused, just come back to the mantra. A pointer is a variable holding an address. Okay, so that's all a pointer is. It's just a variable holding an address. Okay, so in this snippet here, we again initialize our integer x, and in the next line we initialize a pointer to an integer, and the value of that pointer is the address of x. Okay, so the type of this pointer is int star. The int is because it holds the address of an int, and the star that follows the int there, it's called a declarator, the star. It just indicates that this is a pointer. Okay, so the type of pointer is a pointer to an int. So similarly, if you were to define a pointer to a char, the type would be char star. If the pointer holds the address of a double, then its type would be a double star, etc. Okay, so in our toy example, in the picture at the top, again, the value of pointer would be 11, right? Because that is the address of x. It's the address of the first byte of x. So in the definition of a pointer, the star can actually go into anywhere. It can be attached to the the type name, the int. It can be attached to the variable name, or it can go in between. So these are all equivalent as far as the compiler is concerned. So addresses, they can be long and complicated. So usually we draw pointers pictorially, and this is really where the name pointer comes from. We think about a pointer as pointing at the memory address that is their value. So in this case, pointer, it points to the first cell of x. So pointer has the value, so in our picture above, right, pointer has the value 11. That's the address of x, and we can kind of pictorially represent it as the pointer is pointing to the first cell of x. Okay, so here's a question for you. So in this code snippet here, we print out the size of the variable pointer. So what do you think will be printed out here? How many bytes is pointer on a 64-bit machine? So again, pointer just holds an address. So on a 64-bit machine, addresses are 64 bits or 8 bytes. So size of pointer is going to return 8. Okay, so assuming that char takes up 1 byte on your machine. Okay, so now you might be asking, well, an address is just an address. So why, when we declare a pointer, do we have to include the type of the object that it is pointing to? And the answer is that we need to know the type of the object the pointer points to because of another operation that we can do on pointers, which is called dereferencing. So dereferencing a pointer just means go to the address stored in the pointer and get the contents of the object at that address. Now, when we go to get the context at that address, how much memory we need to read depends on the type of the object that's there. So, in a pointer to a char, then we're just going to read 1 byte at that address. Whereas for a pointer to an int, then we need to read 4 bytes starting at that address. So we need to know the type of the object the pointer points to for dereferencing. Okay, now as far as syntax goes, somewhat confusingly, dereferencing is done with a star as well. Okay, and don't confuse this with the star that we use to declare a pointer. It's really 2 different roles that the star is playing. So in this little code snippet here, to dereference the pointer, we say star pointer in the cout line. Okay, and so this is going to print out the value of x, right? Because the pointer holds the address of x, and when we say star pointer, we go to the address where x is, and we get those we get the the value written there, and then we're going to see out that value. So in our picture here, the value of pointer is 11. That's the address of x. And the value of star pointer, the dereferenced pointer, is the value of x. Okay, so here's another example question for you. What is the address of pointer, right? What is ampersand pointer in this toy example in our picture? Okay, so in this picture, the address of pointer is just 1, right? This is the first byte, the address of the first byte of pointer, right? It starts at 1. Okay? Okay, so we can also use a pointer to x to change the value of x. Okay, so here on the third line of our program, we say star pointer equals 5. Okay, so this is actually going to write the value 5 to the address which is stored in pointer. Okay, so in the next line, when we see out x, we're going to get the value 5 there. Okay, so we can actually have the dereference pointer on the left-hand side of an assignment, and then we're actually going to set the value at the address stored in the pointer. Okay, so it's important to keep in mind the difference between assigning to a dereference pointer and assigning to the pointer. So now at the line pointed to by the blue arrow, we actually change the value of pointer, right? So when we initialize pointer on the previous line, we give it the value of x, and then in the next line where the blue arrow is, then we're changing the value of the pointer to be the address of y. Okay, so now in our picture, the value of pointer changes from 11 to 17, right? Because the first byte of y has address 17. Okay, so we can change the address that the pointer points to. That's totally fine. Okay, so after we change the value of pointer to hold the address of y, then in the next line, when we say star pointer equals 5, then this is going to change the value of y. Okay, it's going to leave the value of x alone, right? Because now the pointer points to y instead of x. So when we see out x, the value will be the same as the original value of x. But the value of y will have changed to be 5. Okay, now let me say something about null pointers. So the memory address 0 is special. We're not allowed to access memory address 0. So this little code snippet tries to read from memory address 0. So we initialize pointer to have the value 0, and then we try to dereference that pointer. And this results in something called a segmentation fault. So the code compiles. It's not going to warn you about it, but we get this segmentation fault. Okay, so these are common errors when you're working with pointers. They're really annoying. They can be hard to track down. I'm sure in your programming assignments you're going to run into some segmentation faults. So despite these dangers, we do use pointers with address 0. So typically they're used as sentinel values to indicate when we've reached the end of something. In C++ 11, they actually introduced a new keyword called null pointer to specifically denote a null pointer. And now it's really best practice to use this keyword rather than 0 or null when you want to talk about a null pointer. And the reason for that is because null pointer, it just has one job, and that's to denote a null pointer. Whereas 0 or null, they're also used in other contexts, just to represent the integer 0. So I think it's best practice to always be explicit. If you want a null pointer, use this keyword null pointer. That's really what it's designed for, and that's its only purpose. Okay, so here's a little code snippet example of using null pointer. So we initialize a pointer to the value null pointer. And the next line, this conditional, it's very common logic that you see when you're working with pointers. You don't want to dereference a null pointer because that's a seg fault. So we have this little check, if the pointer is not the null pointer, then we can do something with it. We can dereference it. And then, we could also have an else condition. If the pointer is null pointer, then we might do something else. So this is kind of a common logic that you'll see when dealing with pointers. So null pointer, it can be used with any pointer type, so you can say a pointer to an int is null, you can assign it null pointer, or a pointer to a char, or anything else. It's the same keyword, regardless of what type of pointer you have. So whenever I'm writing code involving pointers, I add another flag to my compilation, and that's -f sanitize equals address. So this enables a tool called address sanitizer, which can be really helpful for tracking down memory errors. So in the example from a couple slides ago where we had the seg fault, if we add this flag to our compilation, then we get the error message that you see here. And what's nice about this error message, that if we look inside of it, it actually, refers to line 7 of our program, and that's exactly the line that was causing the segmentation fault. Okay, so that this tool, Address Sanitizer, can be really helpful for tracking down segmentation faults.